Good morning, ladies and gentlemen. The conference will begin in 3 minutes. Please be seated. Thank you. Good morning, ladies and gentlemen. Welcome to the second sub-conference of the Young Academy of Sciences Summit 2023 to 2024. The theme of today's conference is AI for Science and Engineering. I'm Sabrina Chang, and it's my great pleasure to MC this event. The second sub-conference of the Young Academy of Sciences Summit is organized by the Hong Kong Young Academy of Sciences and co-organized by Greater Bay Area Homeland Investments Limited and the Greater Bay Area Homeland Youth Community Foundation, with funding support from the Innovation and Technology Commission of the Hong Kong SAR government. The organizer and co-organizers would like to thank the following parties for their support, without which the event would not be possible. They are the Innovation and Technology Commission, local academic partners, and supporting organizations, including Hong Kong Metropolitan University, Institute of Professional Education and Knowledge, Ningnan University, the Chinese University of Hong Kong, the Hong Kong University of Science and Technology, the University of Hong Kong. Hong Kong Applied Science and Technology Research Institute Company Limited, Hong Kong Cyberport Management Company Limited, and Hong Kong Science and Technology Parks Corporation and Hong Kong Youth Industrialists Council Limited. The Young Academy of Sciences Summit aims to showcase Hong Kong's advantages as an international science and technology hub and its tradition of excellence in basic research and nurturing young scientists and industrialists. Now, I would like to invite Professor David Lau, founding member and co-chair of the Outreach Committee of the Hong Kong Young Academy of Sciences, professor of the Department of Architecture and Civil Engineering at the City University of Hong Kong, and associate director of City U Academic of Innovation, to give the welcome speech. Professor Lau, please.
Testing. Thanks. Mr. Albert Wong, honorable speakers, distinguished guests, members of Young Academy of Sciences, ladies and gentlemen, good morning. It is my great pleasure to welcome you to the second sub-conference of the Young Academy of Sciences Summits around the theme AI for Science and Engineering. This event is jointly organized by the Hong Kong Young Academy of Sciences, the Greater Bay Area Homeland Investments Limited, and the Greater Bay Area Homeland Youth Community Foundation. As the co-chair of the sub-conference program committee, I would like to extend my heartfelt gratitude for your presence here today indeed. No longer confined to the realms of science fiction, AI has become an integral part of our lives, seamlessly integrating into various sectors and industries, from simple voice assistants to complex predictive algorithms. AI's impact is ubiquitous, touching every corner of our existence. The integration of AI with other technologies, like the Internet of Things and big data analytics, has further expanded its capabilities and applications, making it a cornerstone of the current technological landscape. At this sub-conference, we have gathered some of the leading scientists in the field of quantum quantum science, engineering, and construction industry, who are at the forefront of AI research and applications. We will discuss the latest advancements, share groundbreaking research, and engage in thought-provoking discussions that will shape the future of our disciplines. This subconference is not just about showcasing cutting-edge research or any conceptual theories. It is about forecasting collaboration, nurturing creativity, and inspiring the next generation of scientists and engineers. Please allow me to take a moment to shed light on the Hong Kong Young Academy of Sciences. As one of its founding members, I would like to mention that the purpose of the Hong Kong Young Academy of Sciences is to promote the development and advancement of science and technology in Hong Kong, to educate and inform the public and youngsters on issues pertaining to science. The Hong Kong Young Academy of Sciences was established in 2018. We currently have 61 young scientists dedicated to serving the communities, fostering scientific talents, and advanced science, technology, and innovation. Without a doubt, the Hong Kong Young Academy of Sciences will continually organize science summits and conferences to foster Hong Kong as a center of scientific excellence. Last but not least, I would like to express my gratitude to all of the speakers today who will share their insights with us in a very comprehensive manner. Their knowledge and expertise will undoubtedly enrich our understanding of the transformative potential of AI. I would also like to thank our co-organizers and supporting organizations, particularly the funding organization, the Innovation and Technology Commission, for the essential support. Once again, welcome to the second subconference of the Young Academy of Sciences Summits, where ideas will converge, boundaries will be pushed, and frontiers will be explored indeed. I wish you all a most enjoyable and inspiring day. Thank you.
Thank you, Professor Lau. Now, I would like to invite Mr. Albert Wong, Chief Executive Officer of Hong Kong Science and Technology Parks Corporation, to deliver opening remarks. Mr. Wong, please.
Hello, good morning. I'm happy to see you here. And I'd like to talk about a couple of things. First of all, most of you are coming from local or Hong Kong or from overseas, and the first thing I want to talk about is that if your impression about Hong Kong is all about financial, logistics, tourism, retail, you're not wrong. That has been the pillar industry of Hong Kong for the past 30, 40 years. But we have been starting this journey of change into innovation technology in the past 6, 7 years. So things are going to change, and things have been changing. And the government is committed, not just Hong Kong government, but the Chinese government is committed to making Hong Kong the international hub of innovation technology, the international hub of innovation technologies. And the very fact that President Xi came to this particular place in the Science Park 2022, June 30th, and he clearly said that Hong Kong has to do that. For various reasons. One of them is that we have strong basic research with 5 universities in Hong Kong that are ranked top 100. And our basic research is strong, although we may not be doing as well as Shenzhen in terms of commercialization. So we have to leverage on our basic research. That is why your science and universities are so important. And the other important part of Hong Kong is we are international connection. We are the international city. We can bring people from all over the world, and we will attract talent from all over the world. So this is actually from President Xi, from his very visit 2 years ago. So we are on a path of no return. And this science park is the place to be. I've been on this job for a number of years. This is not a big place compared with China. This is only a 22 hectares, 0.2 square kilometers of space. We've been around about 22 years. And right now, we have altogether about 1,800 companies in this small campus, 22,000 working population. Of the 22,000, about 14,000 of them are research and development. So this is the largest concentration of R&D people in Hong Kong. All right, 1 out of 3 R&D people in Hong Kong will be working in Science Park. This is the community, this is the ecosystem. And by the way, we have 41 restaurants. I think much more than Central. You have a variety of choices, and this is the kind of things that we want to build in this place. We do a lot of things, including we have labs, semiconductor, biomedical. We even have an animal facility somewhere here. I'm not going to tell you which one, but there's a building with hundreds of thousands of mice in it. But these are the kind of things that we do. Communal facilities. We have across the hall. We have AI plug, which is a place for you to share data. Just so you know, we have hospital authority data here. And you may know that HA in Hong Kong has the most comprehensive patient data in the world. And they're available here for people to use. So we are doing all these kind of things. And the other big things that we do is in terms of incubation. We help you with your startup ideas. We have right now altogether about 700 startups working in this campus. And we also have an investment fund. We invest in early stage startup. If you have a startup, we will have money to invest in your company. The latest thing that we have done is that we just sent 5 startups from Science Park to the Silicon Valley. And I asked them, I came back from Silicon Valley in January after CES, and I thought we have to send companies there. And I talked to the companies, the startup in Science Park, and over 100 companies applied for this program. We picked the best 5 and asked them, you go to the Silicon Valley, you work with plug and play for 6 months, don't come back until you're successful. You go there to do your MVP, do your fundraising, do your pitching, do your market development, everything. These 5 companies have been there for 3-4 weeks, and I'm sure they will be successful. And by the way, I have investment in them. So these are the kind of things that we do. We will help all the basic research. We will not be competing with the universities. We don't do the research, but we do the development. We help you do commercialization in whatever way in terms of communal labs for product development, investments, incubation, or even bringing you to the US, to Europe, to even Middle East if you want to go. So these are the kind of things that we do here. And I want you to think about embarking on an R&D journey together with Hong Kong. And I'm not going to spend too much time on AI because I think you are expert. But the only one thing I want to say is that the future has not happened yet. There's a lot of talk about AI. I was with SenseTime just yesterday. They have just launched the Cantonese large language model. I was very impressed. So the future has not happened yet. There will be a lot of things happening in this part of the world, in China, in Hong Kong, and in Science Park. So keep your eyes open. And the last message I want to tell you is that Hong Kong is open for technology, science, and talents. So come work with us and build a better future for Hong Kong. Thank you.
Thank you, Mr. Wong. Please remain on stage. We would like to invite Mr. Wong and other guests to take a group photo. May I invite the following guests to the stage. Professor David Lau, Professor Edmund Lam, Professor Giulio Kilibella, Professor Chi Ying Choi, Professor Jia Yu Chen, Professor Stanley Chen, Professor Xin Huang, Professor Edith Ai, Professor Oscar Dunstan, may I invite all the guests to look at the camera in the front. Maybe let's give a thumbs up and keep looking at the camera. Thank you. Thank you very much. Could Mr. Albert Wong, Professor David Lau, Professor Edmund Lam, and Professor Giulio Kilibella please remain on stage? Other guests, please be seated. I would like to invite the second group of guests to join us on stage. They are Professor Tong Yang, Dr. Jin Xiao Tang, please look at the camera in the front. Maybe let's also give a thumbs up and keep up your big smile. Thank you very much. Please be seated. To commemorate this special event, may I invite everyone to take a group photo. Please remain seated. Our photographer will take pictures from the stage. So may I invite everyone to look at the camera in the front. Yeah, let's give a big smile and keep looking at the camera, please. Thank you very much. Now, let's kick off the first section of today's conference. In this section, we will focus on AI and transformative engineering innovation. We are pleased to have Professor Edmund Lam as the moderator of this section. He is a professor of the Department of Electrical and Electronic Engineering and Associate Dean, Innovation and Career Development of the Graduate School at the University of Hong Kong. He is also the founding member of the Hong Kong Young Academy of Sciences. Let's welcome Professor Lam. And I'll now hand over the time to Professor Lam, please.
Thank you. And good morning to you all. Thank you very much for coming to this section, coming to the whole symposium. But for this particular section, I'm very excited to put together the title of this section is called AI in Transformative Engineering Innovation. Now, this, of course, is very broad, and we know AI is very broad. AI sort of started from engineering and computer science and has a lot of impact in very wide array of aspects. It's certainly transforming a lot of applications, engineering applications. So I have a hard time selecting and putting together, but I'm very happy to let you know that I succeeded in inviting the following three speakers who are going to give us a sampling of how AI has influenced different aspects of engineering work. Right? So the first talk is by Professor C.Y. Choi from Hong Kong University of Science and Technology, Department of Electronic and Computer Engineering. He has been there for a long time, and in addition to being a faculty member in that department, a few years ago he started, and so he was the founding head of the Division of Integrative Systems and Design, a very innovative program to foster hands-on activities and innovation in the among the undergraduate students. He is also the director of entrepreneurship education at HAUST. And another thing that he, among the various things that he's involved in, is he also manages the AI Chip Center for Emerging Smart Systems, which the office is actually upstairs in this building. In terms of his research interests and activities, he has been doing a lot of work in AI hardware accelerator, baseband, application-specific integrated circuit, computer architecture, embedded systems, energy harvesting, and IC design systems. Some of the things I took from his website. But without further ado, let me invite Professor Choi to give you the interesting talk. So my part is boring, so his will be more interesting. Thank you.
So thank you, Edmund, for the introductions, and also thanks for the Academy to invite me to come to give a talk. So I'm not qualified to join the Academy because I'm too old. Yeah, I'm not young anymore. But actually today, today I think we would hear a lot of application of AI in different fields. But the first thought we talk about is not about applications, but about the enabling technologies for all the AI to apply in different fields. Is the hardware design that enable the AI computations on that. So we'll talk about how to do a design of hardware accelerator for AI. In particular, I will introduce some of the work in YASS. YASS is actually an AI chip design center for emerging smart applications, which is one of the Hong Kong projects. And we have we're actually including many universities in Hong Kong and also overseas universities. And we have an office in the 8th floor of this building that houses about 30, 40 full-time researchers and engineers. So I'm going to talk a little bit on that and also talk about some of the key technologies that require for accelerating AI computations. So we all know that AI is everywhere now. So especially there's a lot of breakthrough AI-powered application from like 10 years ago, all the DNA-based applications on image classifications, object detection, speech recognitions. And now we have all this generative AI, so with OpenAI and ChatGPTs. This actually influenced our world a lot. And probably we'll see a lot of applications that you're using all these technologies in different fields, including architectures, constructions, and biomedical application, and also normal people's daily life. So we look at actually, so neural network or AI is basically trying to mimic our brain. So most of this is actually a very rough model about deep neural networks, so that we model the deep neural network with actually some neuron and also synapse. And the deep neural networks basically is connect many these artificial neurons together through multiple layers in order to actually do some very intelligent things, including, like, for example, image recognitions on that. So the computations mainly on this part is actually mimics the computations of the neuron that take in some of the input from the previous neuron going through the synapse and then multiply by the weight with the synapse. So this is a basic computation of the neural network. But the problem is actually for the modern neural network models, so the number of layers is very deep, and also the number of neurons is very large. So for example, so this is actually a graph is mainly on DNN. We're talking about like a VGG19, we're talking about 155 million parameters, that means which we need to use in the network to do computations. And if we extend to the large language models that we are familiar with now for the ChatGPTs, we're talking about billions, and for ChatGPT, it's over 1 trillion type of parameters for that. So with that means what? That means actually when we do both training and inference of the AI applications, we need to assess this so much amount of data that need to store the parameters and also do so much computations on that. So that's the previous one is actually the parameters. And also the computation power requirement is actually increased very significantly. So this is actually for the DNN part. This is like the current large language models that we talk about, not billion flops, not trillion flops. We talk about petaflops, cetaflops, that kind of requirement in order to train. And even for inference, you still need teraflops type of computation power in order to be actually successful for the applications for that. So this is just for inference, not training. We have some training numbers here. So it's a different type of model from like the VGG19 to GPT-4. If you talk about many, like a training, we talk about like 10 to the power 25 flops together. That's inference is about 10 to the power 12 for that. So I don't have any number for GPT, but I only get the numbers that they need 128, so 800 GPU to do the inference. Okay. Now, with that, so actually, with that, why actually we have so good performance in AI in the past, like 20 years? So one of the things actually is two enable factors. One is the big data. The other is the increment or advancement in the computation power that provide. So due to the advancement in semiconductor technologies, due to the advancement of computer architectures, due to the advancement of the circuit design for all this. Yeah, so with that, so we can predict so that actually the computation power requirement become higher and higher, especially when we try to expand the performance or the competitiveness of the AI model for that. So from ChatGPT-4 to ChatGPT-5, and later we talk about general AI, so that kind of computation power will be very explosive for that. So we can think about, so for the whole AI eco-cycle, so we actually have application, which is a lot of you are working on the AI applications, how to use AI in a certain applications. And then we have people like, or the CS guy, looking at how to design the network, how to design the algorithms, how to design the coming up with the new transform model or new type of model for that. And then the underlying part is the computation power. So what kind of chips, how do we design chips that can provide that kind of power to actually enable the AI application to run in the real life for that. So we say actually now the computation power become the bottleneck for future AI development because many people working on AI applications. I think all of us sitting here are working on AI applications. You come out of different applications from every day. So, but the problem is all these applications will still rely on the good network and also rely on the good computation power to do it. So now somehow if this cannot catch up with the advancement of the applications and algorithms, then will become the bottleneck of the future applications or evolutions of AI. So we look at the AI value chain. So we have people working on solution applications, on data, on algorithms. So on hardware, so we have people working on semiconductor process technologies and working on CPU architectures on that. So a lot of this, you see that actually like NVIDIA, Intel, they're working on the problem how to try to push the computation power into the limit. But somehow there's some actually an area that we need to design special type of AI hardware that for special type of AI applications. That actually open up some of the opportunity for startup, for new company, or the new opportunity for people to go to this market, because it's very hard to compare NVIDIA. Yeah, so they have such a strong team. They're the richest company in the world. So with that, so we're looking at like for what NVIDIA is doing, for example, so they're actually trying to target for all the computation power that provide the basic infrastructure for training. So this is the data centers that used for training. So this is the newest NVIDIA Blackwell chips just announced 2 months ago. So they're actually probably the one, I don't know where is the fastest one, or actually also the most computation power intensive one. They can actually provide 20 petaflops kind of performance for each chip. But what's the problem? They're consuming 1,200 watt for that. So if you do like a ChatGPT's trainings in the CPU, so you need actually thousands of this kind of GPU to run. That means actually talking about hundreds of megawatts. But if you use this one to other purpose, like for example, use in autonomous driving car, 1,200 watt is a lot. So that means your battery cannot run, your car is supposed to run at 300 kilometers, you can only run at 100 kilometers because most of the power is supplied by the GPU. So then open up actually a lot of areas, because actually when we do applications, so there's really a lot of different type of applications that do not need that kind of power, but you still need to have a certain power to run the AI applications. So that's actually what our focus is. So we want to look at like not provide the general most powerful GPU tool for training. We want to looking at the ubiquitous AI applications that actually move all the AI applications from cloud to the edge. So why we want to move them cloud to the edge is the following. First, is the latency and response time for that. So now if you want to do like a inference in the cloud, you still need to go through the network, wireless network, and then compute coming back. You have latency issues here. Second thing is about data piracy. So you don't want your data to leave your own device. You don't want to go to cloud and coming back for that. And also cost saving. So you do not want to actually rent the very expensive cloud service to run the AI applications. And also we have other applications like IoTs and also wearables. They all, and embedded AI, they all actually require to put more smartness, more intelligence there. So with that, so we want to actually move the application from the cloud to edge, but there's a lot of constraint here. One of the constraints is we still need to provide a certain amount of computation power and also a certain amount of storage, which is actually impact the cost, and also we impact the power consumption. So one of the issues is the power consumption. If your chip actually consumes too much power, so it's a lot of time, for example, you want to put IoT, you want to make a smart sensor, so you only can be powered by the battery. Okay, so with that limitation, so then you cannot afford to have a very powerful chip that actually consumes a lot of power. So with that opened a lot of applications. So we want to, if we realize these visions of ubiquitous applications, then we need to actually look at two things. We want to improve the AI hardware performance and energy efficiency by magnitude of order 1,000 times for that. We also want to reduce the cost of making special design chip for applications. So with that, we need to accelerate the AI design productivity and time to market for the chips. So for example, So you don't want to spend 3 years to design a special AI chip for certain applications. We want to cut down the time to maybe 6 months to 9 months. So with this, actually, that motivated us to work on this. Then we formed the YASS centers, the AI chip center for emerging smart applications. So it's an innovation, it's an Hong Kong research centers. We said we started in like September 2020, so that is about like 3.5 years. So we are looking at a few areas. The first is actually integrating some emerging technologies with, and also into the silicon CMOS chips that we are familiar with. So emerging technology, including emerging memories. So later I will talk about some emerging memory examples, like the RAM, so resistive RAM. And also we want to integrate the silicon photonics to reduce the energy for communications. And also looking at 3D stacking technologies that can actually provide a lot of parameters and also high memory bandwidth to the computations. And also we're looking at some what we call memory-centric architectures. Because most of the time, the most energy consumption part of the computation is not the computation itself. It's actually getting the data from the memory to the processor to the computations. So in order to actually reduce or optimize the energy consumptions, we are actually looking at some memory-centric architectures. That means you compute within the memory. So you don't take out the data from memory and send it to the processor to compute. Instead, you compute inside the memory for that. And also, we are looking at actually designing design methodology and tools to automate or to optimize the process of designing the chips. So it is actually related to design automations. And also, all this will be integrated into what we call a design flow or optimization framework that actually take into the applications, take into software and hardware together when we design the chip and also the system. So this is actually a joint effort. It's not only from USC. It's actually involving like Chinese U and then Hong Kong U locally, and also some overseas universities, include EPFL, ETH, and also Notre Dame universities. In the past few years, we also work with Stanford together. So there's a group of like 32 faculties. Currently, we have 32 faculty working on different area of this aspect on that. So Edmund is one of our members on the center. Yeah, so this is actually the 4 area we want to look at. So first is emerging technologies. Second is about the architectures of the heterogeneous system integration, the advanced circuit design for that. Third is about the EDA, the design automations tools. And the fourth is actually working on special application, including medical area, including federal learnings, including securities, all this together. Yeah, so that's a summarize of what we have done in the past 3 years. Is actually we actually looking at different aspects for that. We have a paper is standard, and also is some actually best paper competition award, and then some competition. So I think the most important thought is actually this center is on the chip design. So therefore, we really design, fabricate, and test and demo the chips. So we actually have taped out 11 chips, and then we actually have a few different demos we running in the design centers on that. Yeah, and with that technologies, we are actually spinning off from one company, working on especially for chip for large language model for transformer for that. Yeah, so putting transformer or LLM into the edge. So this is actually the company's about. Now, so let's look at actually, well, this is a goal, but what kind of problem we're looking at? So if we want to look at what's the key hardware challenge of computation, AI, or machine learning tasks, there's a few following. First is the memory wall issues. Memory wall issues actually is what? So remember the parameters of the model become larger and larger, is it? So we need to take the data out, we just store the data. So that we have huge data. But at the same time, for computation, we need to take many, many data at the same time. So this is a bandwidth issue. And also, it's a power issue. Because if we store the data in the memory, the power, later we give it some number, the power to get the data from the memory is much, much more than you compute it. Okay, then this is what we call the memory issue. And then because of that, and also how to make it faster. So how to actually, so we talk about requirement, we talk about teraflop or petaflop or zettaflop requirements. So we need to actually raise the performance of the chips. And then, so energy efficiency usually in the industry we measure by TOPS per watt. That means for each watt, how many operations you can do. So we need to, especially for ubiquitous, for AIoT, that kind of applications, we want to have a very high energy efficiency, and also long design time, and also a large model of data size for that. So with that, so our approach is, we believe that we need to actually looking at it not from a hardware point of view. So we don't call ourselves as a hardware research teams. We actually looking at it from a system, an overall synergetical system, network, and hardware designed together. Previously, so there's a general, when we run AI tasks or machine learning tasks, previously we have a processor in mind, and then we try to optimize the algorithm running in this special, run this in this general purpose GPU. But then, so later we actually customize the hardware because actually AI computation is very specialized. Yeah, so we don't need to actually have a general purpose processor. Instead, we can have a customized hardware, but still actually we just using your algorithm mapped to it. But this is an improvement on that. But more important, we need to actually customize hardware and also customize your machine learning applications. That means your network. So you need to design your network, take into account your hardware. So otherwise, it won't utilize the full capability of the hardware, and then you won't actually have the optimization part for that. So now we are actually looking at this as a whole, that is an integration together. It's not adaptation, but the whole process of design the hardware, design the software, we design it all together. Okay, so that's the most important part, so to achieve the goal. So with that, we believe that using this approach, we can help to address the problem of design hardware using for the AI applications for that. So just some basic on the computation part. So usually, so we represent by this neural network, but we get and then so each neuron is doing this computation mainly is on what? It's like multiply the input activation by the weight and summations of that. So we can actually model it as a vector matrix multiplications or matrix multiplication for that. So therefore, the most common, the basic unit of computation is doing multiply and add, what we call MAC, multiply and add. So now, we measure all this kind of performance. Usually, the processor come to give you how many flops is in terms of how many multiply and add we can operate together. Now, so that's actually the two different issues we talk about: the memory issue, a large amount of data and weight, and also the data movement is very hungry from, especially if you need to store the data from off chip. You're not storing the data on the same chip with the processor. You need to go out to read it. It takes a lot of time and also long latency and also high power. And also limited bandwidth because even you have many processors you can compute at the same time to increase your performance. But if you cannot provide the data, then you waste the processor element. So therefore, bandwidth is another issue. This is about memory wall issue. Power issue is on, you have many operations. So for all the neurons, every neurons, you actually need some the weight and some the weighted activations together. There's many computations. So there's a power issues on that. So in order to address these issues, there's a few, let's see, there's actually a few approach we can use. One is basically a complexity reductions. That means we reduce the number of operations. Okay, that means we reduce the complexity of network. Okay, then we can actually have a different method. One of the very common method and also very effective method is what we call network compressions. Because AI, or probably we all know that this actually is not exact computations. It's a statistical computations or approximate computations. So you don't actually, sometimes you don't need to do all the computation, or you don't need to do all the computation accurately in order to get even the good result for that. So with that characteristic, we can actually try to working with the network together and then with the hardware together to compress and then to minimize the amount of computations and also the movement of data. The other type is, the other method is what we call new computation paradigms. It's basically, we just talk about, So one of the issues is the memory issues. So we want to actually reduce the energy consumptions and also the latency of reading the data from outside memory into the process element. Instead, we change the computation, we change the design of the memory, make the memory have the capability to do computations on that. Okay, so actually we can use different type of memory to do this computation in memory. So I will introduce some different type of memory. So you can do these calculations on that. So actually, what we talk about network architectural design is that you have an original network, but doing optimization of network, you can actually do some optimization of network. You can actually do what we call some compression or what we call some pruning. That means some of the weight or some of the neuron you can remove from the network without affecting much of your algorithm performance. At the same time, we design specialized hardware architecture that can be suitable to run this optimized network together so that you can obtain the most optimal solutions. Yeah, so with that, there's actually many techniques be developed and for actually these network compressions, so including network pruning. Network pruning means actually you can prune, you can take away some of the neuron, you can take away some of the weight between the neuron, then without affecting the accuracy for that. So we have different type of pruning method, from filter pruning, from unstructured pruning to structured pruning. The other type is what we call bit precisions. So now, when we do the computations, we need to represent the data. It's a number. So how many bits do we need to represent the data? Okay, the more the bit, the more precision you have, the higher accuracy for that. But because of the characteristic of neural networks, so you do not need to have a very accurate computation for some. For some calculation, you don't need to be accurate. But some, you need to be accurate. Then you can actually use different type of bit precisions. Sometimes you can use, like for standard, we use a 32 a bit of floating point. That means we use 32-bit number to represent a number. And then, but this is maybe too much, because actually the more bit width that you have, the more data you need to store, the more complex computation you need to do. Okay, so by actually using a lower bit representation, so some of the data I can use only like an 8-bit or 4-bit, or sometimes you only using 1 bit, it still work for some of the network, so some of the data for that. How to decide, get which data, which layer of the network use what kind of bit precisions. So that's actually a lot of research work and then develop on how to decide that. And also we can do knowledge distillation based on the previous network, and then we train or we compress the network to a more smaller one for that. So mainly I will talk about this too a little bit more on what we have done. So what we do is that we combine search for the model compression. We do the channel pruning and also precision condensation and sparse pruning, and then adapt it to the hardware, and then coming up with the chips together. Then each network that we actually can map into the hardware can go through this process to fully utilize the hardware capability, then also to reduce the complexities on that. I'll quickly go through, probably I won't go through it, so and on this compression. So we have two types of compressions. For example, we represent the weight of the neural networks using a matrix. So basically some of the weight can be very small. We don't need to store it. We don't need to use it. We don't need to compute it. So then by putting it, and then we can compress the weight into a smaller matrix on that. So then you do not need to store all the data for that. I'll skip some of the, but at the same time, after you do the pruning, because actually your data is changing, your data structure is changing, your way of data flow is changing, you need to design the hardware that can support this kind of pruned network for that. So we have a different work on structure pruning and unstructured pruning, and also designing, so I've got the details on this, and then designing a special hardware to do that can facilitate the pruning. Because otherwise, if you prune it, if you're not actually facilitated, you're still using the old type of process element, it will not give you a lot of benefit for that. Because if the pruning structure or the sparsity structure is very random for that. So we need a special designed hardware that utilize the sparsity characteristic of the neural network. So this is some of the result that actually, but I will skip off that. And then the second one is about the mixed precisions we talked about. So you can use fewer bits. So actually, there's different number of representations we can use. We can use floating point. You can use integers. So you're using 32-bit, 16-bit, 8-bit, or even 4-bit on that. So some actually using binary. So how to decide which weight to use, which bit positions, that needs a lot of algorithms to decide to search for the right combinations so that you can reduce the number of bits you need to store to reduce the memory requirements, but at the same time, you won't lose your accuracy or performance of your overall applications. So we have actually quite a lot of work on doing how to actually decide the bit positions on that. Altogether, we package all this networks compression into a set of tools, including what we call the AI design tools, and also with a special hardware design architecture template. So we build it into we call it a hardware application algorithm hardware co-design platform. So with that, the user only need to give your application of your original networks. You're running all the tools to do the pruning, to do the optimization network, and then decide which hardware platform you want to use. Then we actually directly map your application into the hardware, and then coming up with the chips on that. So this is the design automation part that we can actually optimize it to coming up with a very, very fast way to design a chip and also good performance. So this is some actually example that we are doing. So this is one chip that we take up using the tools together. So we get a much better performance for the existing commercial chips. And this is some of the demonstration. We use chip prototypes that use in like ultrasound imaging segmentations that we store the design into the machine itself. It's not going through the cloud. So this is also using an AI dongle for ECG analytic, the real-time monitoring. So this is for virtual staining for like cancer surgery, for head counting, for AIoTs, for wellness analytics for elderly healthcare. So we're all using the chip that we actually designed to map these demonstrations on that. Yeah, so this is an application, so probably a skip that. Yeah, so this is the second chip. It's actually where we have designed, we finished design, we just send it out for fabrication. It's catered for transformer, for large language models. So the previous one is for DNN, CNN. So this one is for large language model for how to put a large language model into the edge for that. So the chip will be coming back in like in 2 or 3 months, so we're going to test it. So if we have some result, we can report again to you again. Now, finally, I want to talk about some actually new paradigms of computing. We call it compute in memory. So I still have maybe 5 minutes. So the memory was issue. This is traditional von Neumann architecture. That is the processor we are doing right now. So your like a cell phone processor, your PC is all based on this architecture. So we have a processor here. Then we have some on-chip cache. We have off-chip object memory. In order to do computations, you need to get the data from the memory, send it to the processor element. This processor element means I have some adder, some multiplier, they do computations. After computation, you store back the data in the memory for that. So this is a traditional way to do computations. But when we break down the actually energy consumptions for when we run this computation, then to do our MAC, multiply and add operations, you can see that actually most of the time is what? You get the data from the cache or get it from the register file. The operation is only take this. This is the energy that you consume to get the data. So again, so this also summarizes a table. So if we do an add or multiplication, so this is the energy we take. But if we want to get the data from the memory, if the memory is inside the chip, it's 100 picojoule. If outside the chip, it's 2 nanojoules. It's about, when you compare this multiplication, it's about 2,000 times more energy for that. So then actually it's what we call the memory wall issues. So now, how can we tackle these issues? So we tackle the issue by actually changing the model of computations. Instead of you get the data from external memory, you actually you can have 2 things. One is called processor near memory. So basically, you have the memory here, your processor here, very close. But more important, actually, that's the trend that we are actually developing is what we call in-memory processing. That means the memory itself is the computation is done in here. Yeah, but the interesting is actually because we only want to look at the computation that's useful for AI. We are not creating hardware for general purpose. For AI, remember what the computation is what? Mainly is on multiply and add and accumulate it. So with that, actually find, oh, we can design the memory, or we can change the memory structures to do the computation of MAC, multiply and add computation inside the memory. So that's actually create a lot of opportunity to help us to reduce the memory energies is actually 2,000 times more than the computations. So that's actually the idea of what we call CIM architectures. There's a whole chip, so each macro is a memory modules, or we call it a CIM, computing in memory modules for that. It will be it can be different type of memory. This one is show like SRAM. So this SRAM memory is actually we store all the weight here. And the input will be sending out as input. And when you send the input to the memory, it will directly compute here and get the data out. Now, how do we compute? Now, remember, this is the basic computation we need to do. Now, first, we are introducing a new type of memory called RAM. So emergent memory called RAM. So RAM is actually, it's not really new. It's already like 20 years research. So the original research is used to try to replacing the flash memory that we have. Flash memory is what our SSD. We call it non-volatile memory. Non-volatile memory means when the power is gone, the data is still there. So it won't go away. But the current flash memory, the problem is that, so it's slow. So read speed and write speed is slow. Okay, so even it's non-volatile. But RAM is actually, when we do research on RAM, we want to make the RAM fast, at the same time it's non-volatile. Fast in the sense that actually you can read the data in only a few cycles, you can finish it. So one of the emerging memory that try to solve that issue is what we call RAM, resistant RAM. It's basically you store a 0, 1 by changing the resistance of the device. So this is actually a kind of like a metallic oxide device. By applying voltage on these two nodes, you can change the filaments here, and then you can change the resistance. And after you take out the voltage, the filament is still there. So the resistance can be high, can be low. You can program it according to the voltage pulse on that. You can program it to a certain resistance. So if a high resistance, we can treat it as 0, low resistance as 1. And then when we actually have these two, this is the device. When we have a bar coming up, a bar coming down, so this will become a memory device. So we can restructure the whole thing as a crossbar. Every cross point is a memory unit for that. So it's actually, you can buy it from TSMC, from Intel. You can buy this RAM now. But with this RAM, you can actually use it for computation. How? Well, the advantage is it's very high density. Actually, you can do many bits with a small volume for that. So because it's cost-fight issues. Now, we can use it as a computation for Mac. So remember, this is a computation that we have. We need to multiply and then summation together. So, but if we can program the resistance of the RAM, totally program the resistance as a weight. One of the ways to be exactly, the conductance with weight. And then we can model your input as a voltage here. Then the voltage times the conductance become the product, is it? Then each one is a product. And I apply a voltage in this bar. This is the second product. This is the third product. The current flow here is summations of all the product together. So by having an array like this, you apply your voltage as an input. What you get here is the summation of the partial product in the vector computation for that. So with that, you don't need to move the data at all. It's actually using the compute. You only need to program the resistance into a certain resistance that represents your weight. So by doing so, it's actually you can do a very fast, very compact computation, and also very low power because you don't need to move the data. Yeah, so that's actually a lot of people have done research on the past like 10 years, how to use RAM for that. But there's some advantage and disadvantage. Advantage is very high densities, non-volatile, using very low voltage, and then computation in situ. You don't need to move data, and a lot of parallel operations. But the RAM devices still actually have lots of things you need to work with. One thing is actually limited precisions. How many bits we can represent the rate? So how many resistance we can program it in a very exact way. And then second thing is actually this all analog, what we call analog computations. This because it's all in current continuously. We need to actually convert it back to digital. when we actually use it for other computations. So there's some overhead for like what we call analog to digital conversion and digital analog conversion for that. And also, when we try to program the weight, the energy is high. We need to have a lot of energies. But the most important part why algorithm is still actually is a research part, is not commercialized yet, it's because of variation of use. So to program each resistance to very exact value is very hard. And sometimes after you use for a while, the resistance will change. So all this will affect the accuracy a little bit for that. So therefore, this involves a lot of research on people doing the device, how to make it more stable, and people doing architectures, doing how to make it like a tolerate the variability for that. So this is some of the work we did actually, how to compensate for variation. If the variations for the RRAM, but we can still use it by doing some compensation schemes on that. I won't go into the details on that. So this, you can see that actually with some sort of variation of the resistance of the RRAM, you can still get very high accuracy for that. But then, so RRAM is good, very low power, very fast, very low high density, but the problem is the maturity, so the variability issues. So now currently, so if we want to use existing technology to use CIM, what can we do? So now we are based on something called SRAM. SRAM is solid RAM, that is the memory that we use in our chips, existing chips for that. Okay, so this is very mature, everybody is using it, we've been using it for 40 years. But we can also changing this SRAM into a CIM, a computation in memory model for that. So we can do it in digitally, so this SRAM cell, we can do it in digital, that means actually represent every bit as a digital value and then using logic to compute. Or you can do it analogically, so you can actually using it to control the current to do that. So both can be done. So this one, digital, is the, in the commercial world, this is more convincing because actually you can do without any loss. So digital computation is actually very accurate. Analog computations, sometimes you have a loss on that. So therefore, a lot of people are working on this DSIM. We have been working on this also. There's a different, I won't go to the details on that. So this is some of the DSIM, SIM we actually work on in the center. So this is some of the chip we actually fabricate. So now, so what we want to look at is actually this top. Well, I talked about these tops before, is that we want to achieve very high energy efficiency. So remember in the number I gave you for NVIDIA's chip, 20 petaflops at 1,200 watt. The top is about 20 tops per watt, you divide by it. So, but with this kind of scheme, we can achieve very high tops, about like 5 times more than that. So that with that, we can actually utilize it in like for IoT applications. Yeah, so this is another chips that we designed is for like doing some other neural network called spiking neural network that used for like a health ECG applications on that. So this, we also have actually some tools to help us to design this CIM automatically and generate the design automatically for that. So the last slide is actually some of the most recent work we're doing. So remember, so we have the CIM, we can use RRAM, is it? We can use SRAM. SRAM is mature technology, but it's much larger. So you cannot put a lot of data there. But RRAM is very high density. We can put a lot of data in, but it's not mature. Now, how can we actually get the advantage of both? So then we are actually working on what we call hybrid design. That means actually on different chip, we have both RRAM and SRAM inside it. So the two ways we can do it. One way is actually we can do it RRAM store as mass data storage to rate. You read the data from RRAM, go to SRAM to do the calculations. So this is one of the chips that we actually, our partner Stanford actually designed this. And the other way is actually we're developing right now is what we call the fine-grained hybrid integrations. That means for every unit of cell, we have a certain number of RRAM, we have a single SRAM. And then when we try to get the data is mainly stored in RRAM. When we do computation, the RRAM will move the data to the SRAM. The SRAM will do the computations. SRAM do computation much more accurate for that. So this is the current actually work we're working on how to integrate these two technologies together. So, sorry, it's over a bit. So that's actually to give a rough summary on what we have been done in the last 3 years. And I think this is still a very exciting area because actually, so the hardware part cannot catch up with the software. So we need to do more part on that. So also, we actually, when we do the design hardware, we need to work with the application, and also the network design people together, because that's actually so the computation requirement. How can we adopt or adapt the hardware to actually get the most optimal result out of the newest development of applications is important. Okay, so that concludes my talk. Thank you.
We have time for one quick question from the audience. Maybe I ask one thing. You said that a lot of us are doing AI applications, not so much on the hardware, but you made a very strong statement, an argument that the computing is very important. So for those of us doing applications, anything we need to change, anything we need to be more aware of, what goes underneath?
Well, a lot of times when we do applications, so we use some existing network,
right,
and then use the data to train it, is it? So different of data, when you train with network, we have a different actual result. And also we have a different implication on some of the network optimization problem for that. So a lot of times when we do application, we don't actually look at the network optimization part. We just take whatever we have. But so try to actually, there's some tools being developed, especially for if you want to target for a certain hardware. That's better to actually for you to run the special part of the optimization part. That means how to compress your network. So even you use the same YOLO, for example, you actually have different applications. Your YOLO ultimate, the optimal YOLO will be different for everyone. But if you're just using a general one, so you actually waste a lot of your resources in time, in energies, in running applications. So I think this is some of the things. So for people, there's two different layers of people, AI researchers. So one is doing applications. They just treat it, the AI as a black box, and just run it using your data. But somehow, if you know a little bit more deep into it, so it's actually, it's better for you to try to assess some of the tools to help you optimize your network for your applications. That will help the running time, that will help the energy consumptions for your applications also.
Right, thank you. And I hope with this inspiring talk, we all learn how to make our algorithms better, faster, and more energy efficient. Right, thank you. The next talk, I would like to introduce a speaker, Professor Yidif Ngai, a very good colleague of mine in the Department of Electrical and Electronic Engineering at the University of Hong Kong. The department and I personally have been very fortunate to have recruited her to join. She was formerly in the Department of Information Technology from Uppsala University in Sweden. So we got her all the way from Europe to Hong Kong. Of course, she actually grew up here and all that. So I'm sure she's very familiar with the environment here. Her expertise is in Internet of Things and AI, machine learning, data analytics. She has done a lot of different applications, including something called a Green IoT back in Sweden, which was awarded prize in the Faculty of Science and Engineering in Uppsala University, and also from the Royal Swedish Academy of Engineering Science. And I know that since coming to Hong Kong, she has worked on very wide array of applications, and I think the talk today is also on some algorithms. So that from what CY mentioned, Professor CY Choi mentioned on the computing, now Edith move up a little bit on the algorithms and some applications as well. So without further ado, let me put the mic to Edith.
Thank you very much, Edmund, for the very nice introduction, and thanks for the invitation. It's my pleasure to be here today. So my talk is about towards robust and heterogeneous federated learning. So at the beginning of my talk, I will give a brief introduction on federated learning. So I want to know actually quickly how many of you know about federated learning. Can you? Very good. Yeah, so we have quite many people, but most of them are the speakers. So what about the audiences at the back? So students or I don't know. So not all of you are familiar with that. So we will have a brief introduction. We may not need to go very deep to understand the remaining of the talk actually. Yeah, and then I will talk about the major challenges in FL. In particular, I want to focus on two aspects: system heterogeneity and robustness. I think these are two very important topics, especially it echoes also back to the impressive talk from Professor Choi. So we have more and more edge devices nowadays, so they may have limited capability. So maybe system heterogeneity could be important if we want to adopt different devices, especially on the edge with IoT and edge computing, then they may not be capable of computing large models. And security is important, so that's why I will spend some time on robustness, and then I will conclude it. So I want to start a little bit from the beginning. So traditionally, so I believe that we start to do a lot of AI in the cloud, right? We still do a lot of AI in the cloud nowadays. Yeah, so because cloud has rich computation power, so we have data center and they can do a lot of computation like machine learning model training, which can take a lot of time and computation effort. Yeah, so we have AI in the cloud, which refers to the utilization of AI technologies and services hosted by the computers in the data center. Yeah, so this is still a very common model. So in the cloud, we have data storage, machine learning model training, and we also perform model inference. Yeah, so you know model training, right? We get a lot of input data, and then we need to train the machine learning model. And then after that, when the model is trained, then we just give some input data, and then we give the input data of an image of a cat, then it can output a cat, right? That's the inference part, right? But when we teach the model how to have the ability to recognize or classify an image, then we have to train it. Yeah, the training part is most expensive. The inference part will be much easier. Yeah, so but with cloud computing, then we have a lot of service provider, Amazon, Microsoft Azure, Salesforce, and Google, IBM. Yeah, a lot of big companies providing cloud services for all these. Yeah, so it's the classic model. Yeah, but nowadays, as we all know, so we have more and more IoT devices and edge devices. So edge computing is getting more popular nowadays because we believe that our edge devices, like cameras, for example, or some edge points, they have enough computation capability, especially for doing inference, if it is not for training. So most of the existing edge intelligence or edge intelligent architecture still relies on the cloud for model training. Yeah, but we can now do a lot of inference on the edge. Yeah. So the good thing is that probably we don't need to send all the data to the cloud nowadays, and we can do the inference much quicker on the edge. Yeah. So I remember in edge intelligence, the classic model is that we still do the model training on the cloud. Yeah, but here I want to introduce federated learning. So it is a new machine learning paradigm that enables the edge devices to co-train a machine learning model. So it means the training is no longer just take part in the cloud. Yeah, but actually we can have like a bunch of heterogeneous devices or edge devices to co-train the model based on their local data. So for example, these are the clients. They could be different kind of IoT devices or edge devices. And then they can train their local model based on their local data. And then they can send the updated model or model updates to the cloud server for aggregation only. Yeah, so now the server does not need to host the data. So it means that the clients also can keep their data private, and then they do not need to send so much data to the cloud. Yeah, so this is good for data privacy, and also it saves a lot of communication overhead as well. Yeah. Okay, so it just reminds you a little bit in federated learning. So actually, we rely on the clients to perform local training. Yeah, but we usually, in the classic model, we still need the cloud for aggregation. Because say, there's a couple of devices, and then they train on their local models, but based on only their local data. And then at the end, we want to train a global model that works for everybody. Yeah, then in that sense, then we still have to aggregate their local updates or local models. Yeah, but the good thing is that the data could be kept private. So in the FL procedure, it's like we may have a initialization of the global model, and then based on this, then the clients can perform local training, and then they will have the updated model, like it could be model weights or the gradients to be sent to the cloud, and then in the cloud, the server can do an aggregation, yeah, based on the parameters, model parameters from all the local devices, then combine to a global model. So the goal is to co-train a global model, yeah, from the clients. Yeah, so this is a classic fat average family algorithm. Yeah, so we usually receive a global model that is maybe aggregated model from the previous timestamps, and then the clients will do several steps of training based on the local data, and then it could send the gradient, say the change of the weights of the model weights to the server, and then the server can do a weight sum of the gradients and then update the global model and then return to the clients, and then this process will continue repeatedly until the model converges. Yeah, so it sounds to be a nice model that we can keep our data private in the local devices. Yeah, but of course there are still a lot of challenges in federated learning. For example, what about some of the clients might be malicious and they may not be honest in providing the gradients or the local updates? Yeah, so there's something that we need to think about. Can we provide, for example, some more robust aggregation at the server so we can handle those malicious clients? And data heterogeneity. So you can imagine training a large set of data in a cloud. It could provide high accuracy, right? Because it's centralized training. Yeah, but now if we divide the data set, or we have local data in different devices, and then the distribution of the data could be different in different devices. So, but at the end, we want to train a model that works for everybody. So you compare like combining local models with training from scratch using a centralized algorithm, then of course it could be a challenge, right? Yeah. So it means that the aggregated global model in FL may not work that well for everybody. Yeah, that's because of the data heterogeneity. It's a major challenge in FL. And then the second challenge is system heterogeneity. So right now in standard FL, yeah, federated learning, then it's very, very common that the global model is assumed to be the standard, and then it will be the same as the local models. So all the local models should be homogeneous. Yeah, so this is one strong assumption that we need. Otherwise, the global aggregation could be very challenging, but we will look into that. Yeah. But the same problem occurs, say, we have diverse devices nowadays. So it could be quite hard to assume that all devices can do the same kind of computation according to the model requirement, right? Yeah, and then some other people work on communication overhead and privacy. Yeah, so this is a little bit more illustration on data heterogeneity. Yeah, so when we try to study the behavior of FL, then actually we may look into the IID setting and the non-IID setting. Yes, say, on the data distribution of the local devices. And then we found that actually it's common for the devices to have a heterogeneous data in FL, because you see, say if we have like 10 cameras taking images, and of course the images that they take could be different, right? Maybe some cameras take more images of people, and some maybe more like buildings, or some more dogs or cats. Yeah, so it could be heterogeneous. So it turns out that maybe the model trained by those local devices may be good at different things. Yeah, that's one example. But how can we combine these together? Then it could be a challenge in FL. And if we do it in a centralized way, then it will not be that challenging. Yeah, another thing that I mentioned is model heterogeneity. So here in this figure, you can see that we may have different kind of client devices. So it could be a computer which can maybe compute more complicated model. Yeah, but we may have mobile devices or maybe just a cell phone. Yeah, then they are less capable of computing or training large models. Yeah, so another challenge is whether we can actually generalize the requirement of FL not to enforce all the local device to compute the same model architecture. Can we add some flexibility here? Yeah, so the first thing I want to talk about is system heterogeneity. Yeah, so this is the constraint of a homogeneous model, right? Because in standard FL, then we are actually just do a weighted sum. Yeah, when we optimize the loss function, yeah, on the cross entropy loss. Yeah, and then in the global optimization, it's just based on the size of data in each device. Yeah, but there's no much consideration on the computation resources, yeah, on different devices. So we assume that it's the same model architecture. But if we consider different capabilities of the devices, can we actually consider different model architectures in each local device? Yeah, then if that's the case, then maybe the local clients, the clients could have different model architectures. But then the challenge will be how to combine the local models together. Yeah, so we are not the first the first group to look into this problem. Actually, we find some literatures. For example, this one is quite easy to understand. That's why I picked this one to illustrate. Yeah, so this paper is called HeteroFL. Yeah, so its idea is that we can have a large global model. Yeah, but at the same time, we can enable part of the model, partial models from out of this large architecture, and then to form smaller models for devices with heterogeneous capabilities. Say more capable device can use the whole model, and then less capable device can use a part of the, maybe 1/4 of the parameters, and then smaller devices can consider even less model parameters, and then they will train just a smaller part of the model. So this is one way to consider model heterogeneity. And then there are also a bunch of papers looking into data heterogeneity in FL. For example, this paper is quite interesting because it's exploring these CKA similarities of different layers in different client models. So it gives a very interesting observation. Say in the shallow layer, yeah, layer 1 of the model, then we found that actually the similarities of different clients in that layer is very high. Yeah, but then when we goes on to a deeper layer, then we find that this CKA similarity becomes more different, and then here has very low similarity. So it means that it's a little bit similar to when we extract some features, yeah, from images, for example. Then maybe the edge or those features in the lower layers could share more higher similarity no matter what kind of images. Yeah, but in later, deeper layers, then maybe close to the classification, then we can have more variety, and then the errors will also increase accordingly. So, and of course, this paper, it shows these results, but at the end, later, they also propose some methods to generate some sample data, synthetic data to do the calibration. Yeah, but this is not the focus that I want to talk about here. This is something that inspired our work, actually. Yeah, they inspire us to conduct a case study, yeah, to compare FL in homogeneous and heterogeneous environment. So here, I repeat it, homogeneous means that all the local clients are running the same model architecture, while heterogeneous FL means the local clients are running heterogeneous architectures. And then in our case study, the goal is to observe the performance gaps between homogeneous and heterogeneous models in FL, and then to gain some understanding of the factors that limit the performance in heterogeneous setting. And then we conduct a case study considering both homogeneous FL and heterogeneous FL. Yeah, so for homogeneous, we have a fixed architecture. We consider ResNet 18 and Vision Transformer 12 layers with ID across all clients. And then for heterogeneous, then we have 5 different models with non-ID data across all the clients. Yeah, and then we, similar to the previous paper, we use a CKA similarity to evaluate the layer similarity. So from these figures, actually, for example, this one, we can see that if it is the case with ID data and homogeneous architecture, then the CKA will be very similar across the layers in the clients, especially in earlier stage. Then the similarity will be very high, almost 1, and then it will drop gradually in deeper layers. So this is similar to what we observed in the previous paper as well. Yeah, but in non-ID with homogeneous, then it becomes a little bit more challenging. And then for non-ID data with heterogeneous model, then it will drop even further. So from these results, then we see that this is for ResNet and this is for Vision Transformer, but they have a similar results. So from these diagrams, then we can infer that, okay, maybe this CK will be higher in the shallower layer and much more different in the deeper layer. So can we do something like to use the shallow layer gradients to guide the deeper layers so that we can improve the accuracy of the model in heterogeneous FL? So that's our idea. And at the same time here in the figure on the right, then we can see that if the CKA is higher, then it also brings higher accuracy. So our intuition is that, okay, if we can increase the CK similarity across the clients, then maybe the accuracy will also increase. And if we use the shadow layer gradients to guide a deeper layer, then maybe it will work, yeah, because the CKA will be higher, probably with this alignment. So that's what we are thinking. Yeah, so this is just a little bit more results on the previous conclusion. So, and then in our work, then we propose a scheme called encode aggregation. And then it supports 3 different kinds of model splitting. The first one is layer splitting, so this is the simplest one. So, for example, a smaller model can take the first few layers, and while medium model can take first 6 layers, and a largest model can take the whole global model architecture. And then we can also have stage splitting. So first we divide the model into several stages, and then we take different layers in different stages for different models, local models. And then we can have a combination of a hybrid hetero splitting, combining stage splitting and layer splitting in forming different model size for various devices. Here on in the table, we just show that actually with non-ID data, the test accuracy will decrease, and if it is heterogeneous models, then it will decrease further. So this is actually something that we have observed and also expect. Yeah. And then here in this diagram, it brings an idea of internal cross-layer gradient. Yeah. So we are thinking that we can use the shallow layer gradients to add on to the deeper layer gradients, so that we can have a cross-layer gradients. So after using these cross-layer gradients, yeah, then we can still see that we still encounter the gradient divergence problem as shown in this figure, for example, 6A. Yeah. So, and then that's why we are thinking that we need to do a little bit more improvement to tackle this problem. To mitigate this issue, then we propose a convex optimization problem that restrict the gradient directions. Yeah, so this is something like here. As first of all, we normalize the gradients, and then after normalize, we do an optimization. And we try to guide the convergence of the model are closer to the global optimal. So just a quick summary. So in co-aggregation, our idea is that we want to use gradients as knowledge. So we don't want to use shared data like in some of the related work in order to tackle the data heterogeneity problem. And we also want to utilize features in FL. So we don't want to utilize the features from the earlier layers because this will increase the communication overheads. Yeah, so that's why we just want to propose a scheme that based on gradients. And then we formulate an optimization problem to estimate this optimal gradient. Yeah, and in the same time, we want to guide or constrain this optimal gradient to be more aligned to the shallower layer gradient. Okay. So. And then we conduct some experiments to verify our proposed solution. And then we have 4 different data sets. So I guess many of you are familiar with this MNIST and Cypher 10. And then we have different settings for homogeneous baselines and also for heterogeneous baselines. And then we try to look at the performance. And we see that actually our scheme is quite powerful in a sense that we can easily add on to some existing originally not supporting heterogeneous aggregation. Yeah, so we can update these schemes according to our splitting methods and then with our in-co aggregation schemes to make them suitable for heterogeneous models. Yeah, and then the results are pretty good as well. Yeah, and then if we compare with some other existing heterogeneous setting algorithm, then we can still provide a certain level of increase in the accuracy. So it means that our proposed solution in co-aggregation is actually quite a nice add-on to many existing algorithms. So this is just some ablation study that I want to skip. And then second part about the robustness in FL. Yeah, so now you know how it works in FL. Yeah, then actually there's a problem with malicious users because the clients have to provide this pseudo gradient to the server for aggregation, right? Yeah, but if we have like some malicious clients, then it may provide some malicious gradients that can ruin our aggregated model. Yeah, so how can we tackle this problem? Yeah, so in our work, so we consider some potential attacks, say adding a random noise or a sign flipping of the gradient or label flipping, flip the label of some of the training samples. So can we handle these problems? So how to make the server-side aggregation more robust to malicious attacks? So there are a number of works that are trying to tackle this problem. So some of these are quite simple. For example, Chrome is trying to find one of the local model updates that are closest to another k-m-2 ones with respect to Euclidean distance. And some are based on like a clustering methods calculate the pairwise cosine distance between updates. And some are using mean or trimmed up mean, geometric mean, or a median, etc. Yeah. So we summarize a little bit like the methods they use, and some of them are based on Euclidean distance, some based on cosine similarity, some use a mean or median, and some use clipping techniques. And then we want to give an example on geometric medium. Yeah, so this seems to be a pretty nice scheme originally that aims to find a vector that minimizes the sum of its Euclidean distances to all the updated vectors, right? All the local inputs, yeah. But the problem is that if we have like some malicious clients, then it will still drag the global model to be close to the malicious local updates, right? Yeah, and then we are thinking how to solve this problem. So that's why we think this original geometric medium is not good at handling malicious clients because they just look at the geometric median. Then we make a generalized version of GeoMat. We call it AutoGM that can update the global model more reliably. Yeah, so in this scheme, actually, we consider like a weighted sum of the Euclidean distance, not only a sum. Yeah, and also we add one more term to control like how many data points to be considered in our global aggregation. Yeah, so because say if we have like 2 malicious clients out of 100, and then these 2 are very far from the other provided local models. And then the motivation is that we don't want to consider them, right? Because they will probably ruin our updates. Yeah, for example, in this example, so the red points are the benign local updates. Yeah, but the green points are the malicious ones. So if we just look at the mean or the GM, then we find that it will still drag the model quite far from the optimal here, right? So our idea is that we want to learn like different ways of different models. And then if they are so far, for example, away from the others, then say these are so far away, then maybe we can try to reduce their weight. So you see that this green color is still very bright. Yeah, but if we set different lambda value, then we can actually reduce their weight. So when they are light color, then they have less influence to the global model. So now it's getting close to the optimal. And if we set this lambda to be very large, then actually they become white and they are not considered. Yeah, then we will have like a very good aggregated results. So if we compare our solution with some of the existing works, yeah, so these are some more popular federated learning aggregation algorithm, then we see that actually our performance similar to them in the case with no malicious attacks. Yeah, but we can perform much better in handling model poisoning attack and data poisoning attack, much better than like some of these, for example. Yeah. Yeah, so based on our work on robust FL, we also developed a tool called Blades that we open source to the community so people can download and conduct experiments related to evaluation of attacks and defenses in FL. And our goal is to improve the reusability and extensibility and scalability of this kind of research in the community. So in conclusion, so I talk about like FL and some challenges, and I focus more on the model heterogeneity and the robustness in this talk. Yeah, so I talk about our solution in code that can make use of the different splitting methods and also cross-layer gradients to enhance aggregation accuracy. And for robustness, I talk about AutoGM as an example that can improve and the robustness in model aggregation. So for future directions, then we are looking into like split learning and also different kind of adaptive model partitioning based on available resources. And we are also looking into the impact of foundation models to FL, for example, see if we can incorporate large language model or some other foundation models to support many more novel applications. Yeah, so that's the end of my talk, and I want to acknowledge my students and my colleagues in Hong Kong U and also Uppsala University and also some other overseas universities. Thank you.
Thank you. Do we have any questions from the audience? Yes.
Is there a typical scenario that you have in mind with the data? Is it like medical data, or is there a typical scenario for this?
That's a very good question. So any typical good data. Yeah, so in our simulations, it's largely relied on some existing data set related to image classification. Yeah, so but I believe it could also be extended to other model architectures or applications. But FL community, a lot of people are focusing on image classification. That's why we continue along this line. It's easier to compare with other existing work using the benchmarks. Yeah, yeah. Thank you. Yeah.
Thank you. Any other questions from the audience? Right, if not, then thank you, Yidif, Professor Yidif Ai, again. Thank you. And our third talk is a speaker from overseas. We have Professor Stanley Chan, Elmore Professor of Electrical and Computer Engineering and Statistics from Purdue University. So Professor Chan works on computational imaging. So just after what Professor I just said, the federated learning applications in imaging. So Professor Stanley Chan is picking that up, and we'll talk more about images and vision. His work on computational imaging basically looks at intelligent cameras by co-designing sensors and algorithms to make cameras capable of seeing and having some intelligence in different environments. He has been very active and has received various prizes ranging from Best Paper Awards from IEEE Signal Processing Society to a lot of teaching awards from Purdue universities. I would now like to invite Professor Chan for the talk.
Okay, good morning. All right, it's always a pleasure to be back to Hong Kong. I graduated from Hong Kong U as an undergraduate, so it's really a pleasure. Okay, so I want to talk about diffusion models in imaging and vision. So this is a sort of like a hot topic nowadays. So before I go into the details, let me talk about Purdue University. Many of our students, especially their first time coming to Purdue, they thought that we are a private school, but well, Purdue, where you have a name, it's one of the very outliers in the United States that we are a public school. We are a land-grant public school founded by the Morale Act back in the 18th century. We are located in the state of Indiana. We are 2 hours south of Chicago. We are 1 hour north of Indianapolis. We produced quite a bit of engineers, astronauts actually, including the Neil Armstrong, who stepped onto the moon, the first person to step onto the moon. This is a number that our dean wants to show to people, or whatever. It's number 4 in the US News ranking, whatever it is, okay? You guys interpret it. I talked to Edmund a couple of days ago. This seems to be an important number. Anyway, I work in the field of computational imaging, which is at the intersection of multiple things, sensor design, physical world modeling, especially about wave propagation equations, and machine learning algorithms. Over the past 10 or 15 years, we have been mostly working on 2 topics: imaging through weather, especially imaging through atmospheric turbulence, and single photon imaging, where you can think about time of flight sensors, photon counting devices, very difficult scenarios. But today, I want to talk about something trendy. I think it is a hot topic, it's a sexy topic, it's a topic that I can get more people to come and listen to my junk, so I want to talk about that. I want to talk about generative AI, okay? It's very hot. And if you flip any newspaper, you will see articles like this. This is just one of the many, okay? ChatGPT can nowadays generate images. Of course, we know. We know this a long time ago. But the images are looking pretty good, okay? What else? Well, this is a YouTube that you can go and watch. It's pretty fun. You can type a sentence. Let's say I want the hedgehog, a cartoon that has several small animals playing with the hedgehog. Just type that sentence. There are softwares that are able to generate images like these. Okay, and if you pay attention to the newest updates, you have Sora, which can generate videos. And I was telling my wife that it is a very difficult thing because they can generate fingers very well, and the fingers they're moving. That's extremely hard, okay? If you think about how much fine details you need and how much motion you need to control for the fingers, that's very difficult, and they managed to do it. If you look at money, right, I guess is science part, you want to talk about money, startup, a lot of opportunities because all these giants, they are putting a lot of money behind it. Every big companies, they have a branch or more branches doing generative AI, and so it is going there. So I don't need to do more advertisement, and I think everyone is already very excited. What I want to do is to talk about how this thing works, okay? I am not advertising for any group, including my group, because I'm just starting to work on this. I am not any big figure on this topic, okay? The whole motivation started with some questions from my students. When you're a professor, you hand an assignment to a student and you say, hey, work on this. And then the student would just go to GitHub and download code. And then they go to some blogs and then they repeat whatever the blog says, and then I ask questions and they sort of got lost, okay? So I got really, really annoyed. And so I went to the blogs by myself and then find, okay, why are all these blogs on the internet, they are convoluting? They just repeat each other. Eventually, they're talking about the exact same thing that doesn't really teach you anything. So I got so annoyed that I decided to write my own tutorial. And that's how I got to learn this topic. And so I come up with 5 basic concepts about this generative AI, okay? Now, these concepts, they are not meant to be comprehensive. They are just meant to be introductory. And they are designed for beginners. Okay, so I know in this room, we may have students and researchers, you have been working on this problem for a long time, then you need to pardon me, it is not going to be that entertaining, okay? It's designed for beginners. All right, 5 concepts about generative AI. My goal is to make sure that you know how generative AI works by the end of this 30 minutes. Is it okay? You ready? Okay, 5 principles. Okay, reference, you can go online, just type this tutorial, you can find it. Okay, first principle, generation, okay? Generative AI, of course, we need to talk about generation. Generation means sampling, okay? Generation means sampling. So you ask, what is sampling? Well, let's start with this example, okay? You give an exam to a class, okay, at Purdue, we usually have this kind of distribution. I assume that's the same case at Hong Kong U, right? You have a bimodal distribution. You have some really hardworking students, and you have someone who never study. They have too much activities in their halls, okay? All right, so, well, by the way, I lived in Hong Kong U Hall before, so I know how this looks like. Let's say this is the historical distribution of the class. And now you walk into your section in 2024, okay? You randomly pick a student. You say, what is his or her score? Okay, so pause for a second. This is a generation question, okay? So I tell you that there is a magical distribution, okay? Historically speaking, whenever you take this course, it's gonna look like this. And this time I ask you, generate a score. Generate a score that will represent a distribution like this. Okay, do you get the question? Okay, right, so this is what we mean by generation. So how would you do that? It's easy, okay? So you look at the busy, hardworking cat versus the lazy pig, and then you pick a class, and then you condition on the class, and you say, hey, if this is the hardworking class, you're gonna draw a sample according to a Gaussian distribution with a certain mean, a certain variance. Otherwise, you're going to draw from in the class. Okay? And so the number that you're going to get will be mostly 80 or 40, but you will never, or you have a lower chance of getting 60. Okay, why? Because by looking at the distribution, there isn't anything in the 60, no matter which class you belong to. Okay, so by looking into this histogram or distribution, you will be able to come up with a number that will make sense according to the distribution. And if I can sample from this distribution, I mean, effectively, I'm generating a number. In probability textbooks, we know this for a long time. You can do this easily by using cumulative distribution functions, inverted, draw uniform sample, blah. Okay, you can do that easily. You have formula. So the bottom line message here is that generate a score means you want to sample from a distribution. If you want to generate a word, now word can mean an alphabet, for example, the word sample or the word from, okay? So a word can be multiple alphabets you put together. And here, let's say we put two alphabets into a word, okay? For example, the word is, the word as, okay? So you can have a two-dimensional distribution. That's also easy to think about, right? So you go from a one-dimensional Gaussian to a two-dimensional Gaussian. And you can easily expand it to images. Oh, wow, that's quick, okay? They are also distributions. They're high-dimensional distributions, but they are distributions. So if you want to generate an image, that means you want to pull a sample from the distribution that you know. Okay, so images, they are just vectors in high-dimensional space. I give you an image with a dimension of 224 by 224. You go to ImageNet, you download image, it will be that dimension. You pick it out, and then you stack them into a long vector, okay? And that's just an array of numbers. If you have two numbers, that's called a two-dimensional Gaussian. You have an n-dimensional vector, you have an n-dimensional distribution. Of course, I cannot draw it, so have some imagination. It's something like this. Some images are more likely to happen, and some images are less likely to happen. And therefore, on this distribution, you have peaks and you have valleys. The valleys are images that are unlikely to occur. And therefore, when you say, I want to generate an image, and why are some images, they are so terrible? Because you run into the valley and you pull an image that doesn't really look like an image. Okay? And so some images, they have higher probability, some images have a lower probability. If you have access to this beautiful distribution, in principle, you'll be able to generate any image you want. But of course, in reality, we never have access to this distribution. If you have access to this distribution, you can become a billionaire because you can generate any image you want. And so, generate a score, you need the true distribution. For example, you need to have a formula, so I can run the cumulative distribution function, I can invert it, transform it. Right? You either have a formula or you have a histogram to generate two scores, okay? Or a word, you need to have a formula or histogram. For images, that's very hard. You can never write down a formula. People have been working on this for many, many years since the beginning of time, okay? We have so many different prior distributions, mixtures of experts, mixture of Gaussians, all kinds of models that have been proposed over the past decades and decades, and we never have a formula. And we will never have a formula, let me put it this way, okay? And so, that's a $1 billion question, maybe more than that, okay? So we know that generation means sampling. We know we need to have a distribution, but we never have access to a distribution. And so that goes to the second concept, okay? Which is, what is image, okay? If you cannot have a distribution, we need something else. All right, so concept number 2 about generative AI is that images is representation. Okay, it's a very complicated word, representation. So let me explain this way. So let's say on the right-hand side, you have a dog, okay? That's an image. And then there is a magical neural network that's sitting in the middle. And then on the left-hand side, there is a thing called the latent variable. Okay, so that's a low-dimensional representation of the image. Now, certainly, what we want to do is to train the neural network to convert the latent variable back to the image. Certainly, okay? And this is not magical at all. If you think that, wow, this is the power of deep neural network, let me tell you a bad news, that we have known this forever, okay? So back in the time of eigenface, that was in the 1990s, you want to generate a face image, you just run the principal component analysis of the data set, and then you grab all these eigenbases, okay? And then you put the linear combination of these eigenbases, you will be able to generate image, okay? So all these eigenbasis images, they are known to you, and then only the z's, they are unknown to you. So if I tell you all the z1, z2, all the way to zn, in principle, you can generate whatever image you want, and just flip the z's. And therefore, the z's, they are called the latent variable, and then the reconstructed image is called the x hat. So this is known forever. Now, if you want to trace even further back in the history, we have JPEG. JPEG is even better known that if you crop a patch from the image, every patch can be represented as a linear combination of the discrete cosine basis. We know that. And so if you tell me all the z's, the coefficients, I will be able to generate a patch for you. So there's nothing too magical behind this. Your pink box in the middle, they just need to remember what the basis functions are and then how the linear combinations are done. And so you just tell the pink box the linear combination coefficient, and it should be able to generate the image for you. So that's no dark magic. What basis to use nowadays? Well, you can have a hierarchy of bases. You can train a neural network. You can have layers and layers of representations. And today's backbones, they are very powerful. You can train a common backbone, and then you can put whatever downstream architectures to do any other tasks that you want. So can we use arbitrary backbones? The answer is not quite, because you do want to control the latent variable. Okay? Because eventually what you want to do is to generate an image that you want, and therefore the latent variable has to correspond to the image that you're generating. And we need to have a choice of the latent variable, and the choice that we're putting there is that it has to be a Gaussian, white Gaussian vector. And many people ask, why white Gaussian vector? Okay, if you go to internet, people will just tell you, okay, we have been using white Gaussian vector forever. And some paper says we should use Poisson, some paper says let's use whatever. And here's the 4 reasons I put together, okay? It's cheap, it's easy, it's simple, it's lazy, okay? Nothing more, okay? So don't argue with me. Why don't you write a paper on Poisson diffusion model? Because Gaussian is cheaper, it's easier, it's simpler, it's lazier for me, okay? So that's the main reason why people put together the Gaussian distribution. So what I mean is that you have a distribution that is sitting on the right-hand side. That is a distribution for the dog image. And then you have a magical pink box, which will remember some of the basis functions, and you need to train it. And then you have the latent variable, which is a vector, and that vector is a white Gaussian vector, and that's by choice. Don't argue with me. I'm the designer, I have the choice, okay? And I put it to be Gaussian. Okay, so this is set up, right? So images, they're just representations. Representations, they are remembered by the pink box. Okay, so what is learning? Learning is encoder plus decoder. What I've just shown you is the decoder, and you need an encoder. So autoencoder, which is a concept that was developed about 15 years ago, it says that when you train a model, you don't just train the decoder, but you also train the encoder simultaneously with the decoder. And there is a variation of that. It's called a variational autoencoder, VAE, and that is a sort of the variant that does everything in the distribution sense instead of doing things in the deterministic way. But when you look at this diagram, you can see that there is a pair of neural networks. The encoder, the blue box, does the the job of converting the dark image into the latent variable, and then the latent variable will go through the pink box and then become the dark image again. Now, of course, during the generation process, you only need the pink box. You don't need the blue box. The blue box has to be there during the training. If you don't have a blue box, how can you control that the latent variable would behave like what you want? And therefore, in this VAE setup, you have the decoder and you also have the encoder. Now, without going through 20 pages of derivations, let me just tell you how the encoder should look like, okay? The encoder in the VAE setting, the variational autoencoder setting, after so many years of derivation, people have found this is one of the most effective ways. You take an image in, and then you have whatever neural network you want. Okay, I'm really saying whatever neural network you want. Architecture is not that important in this community. Okay, you put whatever neural network you want, and then the job of this neural network has to not to generate a white noise. Okay, noise vector. This neural network has to generate the mean vector and the covariance matrix of your Gaussian. Why? Because that's a lot easier to generate. Right? Generating the parameter of a Gaussian distribution is a lot easier than generating the noise vector. And so you can generate the noise, the mean vector, and also the covariance matrix. And then since it is Gaussian, you assume that it is Gaussian. You can pull a white noise vector from that distribution. That's pretty easy. After that, you can train your decoder. Your decoder has to take this latent variable and turn it back to the image. This is a network, is a convolutional ResNet, whatever. You put a network over there. And you know, when your network is large enough, you can generate pretty much whatever image you want, right? So just have a large enough network. And then this image has to be compared with your ground truth and then set up a loss, and then you minimize the loss. And then by tweaking your neural network parameters, you will be able to get it done, okay? So here's a training. You train the encoder, you train the decoder simultaneously. And by training, I mean that you update the model parameters of the encoder together with the network parameter of the decoder simultaneously, and let them fight for a couple hours and let the students cry for a couple of days and then never converge, whatever. And after a couple of days, they will get a result, okay? They will get a network, a pair of network, the encoder and decoder, okay? This can be trained. After you have trained the encoder and the decoder, you can give up the encoder. Just keep the decoder. Just keep the decoder. So what you will send to the decoder is a latent variable, which is the vector. If you change the latent variable to a different vector, the decoder will generate a different image. So let's say this vector will give you a dog. You change the latent variable to another vector, that should give you a cat. Now you say, how do you know it's a cat or a dog? Well, that depends on what kind of data that you put to the model to train. If you put the dog and cat images in your training set, of course it will generate dog and cat, and it will never generate flowers. Okay, so the training becomes a very, very big deal in the generative AI. Dinosaur today, breakthrough back in 2013. Okay, you can see that these are the images that people were able to generate using this very simple variational autoencoder method, okay? They are not looking very good by our standard today, but it was a miracle back in 2013. Okay, so concept number 4. What is then a diffusion? Okay, what is diffusion? It's not that magical at all, ladies and gentlemen. It's just a chain of encoder and decoder. If you understand how the VAE work and just repeat it multiple times, that's called the diffusion model. Here is the architecture of the diffusion model. You start with the state x0, which is the image, and then you go through it, and then go to state xt, which is your latent variable. Okay, so if you want to map this back to the picture that I showed you before, x0 would be the beginning, which is the image, xt would be the end, which is the latent variable. You have a chain of operations sitting in the middle. There are some arrows going back and forth. You can forget about them. They're just intermediate state. Okay? They're just intermediate state. So you ask, why don't you just do a one-shot learning from the beginning to the end? Why do you want to do so many small steps? And here's the reason. Small steps can lead to big changes. Okay, so if you're faculty in a university, you know how difficult would it be to make any change in your unit, right? You want to do a little bit of changes in your curriculum. You know how many committees you need to go through, right? So how painful it is. So don't make changes, big changes all at once, because you know you're guaranteed to fail, okay? For example, the trash bags, right? And I sort of keep updated of the news of this government, okay? So you know that. Anyway, okay, so what's the deal here? Well, so you have an image, dark image, and then you have a distribution, which is the Gaussian distribution, okay? And then the Gaussian distribution, by the way, a Gaussian distribution in high dimension will look like something like that, okay? It's just pure noise, okay? It's just a random number, and you have a lot of random numbers, it will look like this. So that's called noise image. So how do you go from a dark image to a noise image, and sequentially, multiple steps, step by step, add noise, okay? That's it, okay? So you start with the image, add a little bit of noise, and then add a little bit of noise. Gradually, that's called a forward diffusion process. Now, of course, there are physics behind it. I will skip that. But that's called a forward diffusion process. You gradually add noise. You cannot arbitrarily add noise. There are ways, there are schemes to add noise. So I will skip that. But I want to comment that the noise there is still white Gaussian, but it's not the noise that you take it from your camera, because the noise is something that you control. It's the latent variable that you control. It's not purely random in some sense, okay? Okay, so if the forward process is to add noise, then the reverse process has to be remove noise. So how do we remove noise? Because it's an image. Removing noise from an image, of course, you need a neural network, and so you put a denoiser. So from x of t minus 1 back to x of t, t minus 2, you have a denoiser. So every step you have a denoiser, you have a chain of denoisers, and then you need to train these denoisers. So here's how things work. You start with pixel space, you go through the latent space, okay? So you have the forward diffusion process. And then when you go to xt, which is the pure noise, you go backward, okay, step by step. You go through for the reverse diffusion process, go all the way back, you get x1. Okay, so that would be the reconstructed image. So results in 2020, that was a miracle. That was amazing, okay? So you can have all these beautiful looking images that are generated by this denoising diffusion probabilistic model. So finally, concept number 5, you have all the building blocks. You ask, how do I type in a sentence and then generate an image? Okay, so you look at this block diagram. You have a forward diffusion process. You have an inverse diffusion process. Let's look at the denoiser. You can replace by something we call the transformer. Now, if you're new to this field, it's easy to go online and find some tutorials about transformers. So there's something called transformer. And in transformers, you can put in conditions. For example, images or text or semantic maps, you can have different things you can inject into the transformer. There are 3 symbols, Q, K, and V. I guess we can skip all these, okay? So they're just the query and the key and the values and things like that. For those of you who do image processing for some time, just want to mention that this concept has no difference than the good old days non-local means, okay? You measure the similarities between the 2 feature vectors. In the old days, we calculated Euclidean distance, but in the attention, nowadays, they just do the inner product. Why inner product? Because you clean it, it's just too complicated to calculate, and so they just take the inner product. And when your network is large enough, who cares? Okay, so that's how things work. From attention to generation, you can type in words. You can have different places of attention. You can generate different values. Okay. Okay, so a generation hierarchy, you can go from the text, you can generate a small image, okay, so that's the text to image generation, and then you can start to do the super resolution generation. So from a smaller resolution to higher resolution to very, very high resolution. So to wrap up, there are only 5 principles. Okay, that's all, okay? If you ever get confused about generative AI, these are all, okay? Generation means sampling. Images are representations. Learning is encoder and decoder. Diffusion is just a chain of encoder and decoder. And image and text conversion is just conditioning. You put a condition into the transformer. Okay? And that's all. Okay? Now, of course, you can add a lot of salt and pepper and soy sauce or hoisin sauce, whatever, to this main ingredient. But you know what I'm talking about. Okay? So now if you can do images and videos, you know you have solved the most difficult problem in the earth, okay? So you can do generative AI for price data, weather data, medical data, cow data, whatever you want, okay? So you can do it. There are many exciting opportunities. You can go for virtual clothes. I guess my wife will really like it. I guess Edmund really liked this idea, AI-generated proposal grant writing figures, okay? And the value proposition for AI, generative AI, I think, that's really my personal thinking, is personalized assistant. I have a good friend at Purdue who self-taught himself Python programming, and then he has a Python sitting here, and then he types some code, and then he asks ChatGPT, did I make a mistake? Syntax error, can you help me fix it? And then ChatGPT fix it for him, okay? And he can generate a lot of homework assignments for the students. So I think this kind of personalized assistant is pretty good. It's pretty powerful. It's pretty good. It's like hiring your personalized tutor sitting right next to you to teach you how to write programming for free, okay? So that's a pretty good deal. Data synthesis, if you ever do image processing, you need a lot of data, so this could be a good source of data. Open problems, I think it is just the beginning of this revolution. There are lots of problems. These are just some of the problems that you will be seeing a lot more in the coming few years. Multimodality, fidelity, deepfake, inconsistency, slow. You need a lot of training data. We don't have enough training data and things like that, okay? So for this, I will stop here. I will take questions.
I'm sure that generates a lot of exciting questions from you. So may I invite the audience for questions? Otherwise, we have to generate some. Right. Sample your questions. Just inject some white noise and they become intelligent questions for him. Right. So maybe I'll ask some white noise type of questions for you, right? So in terms of applications, so you mentioned about personalized assistants and all that. So how about robotics and how does these generation, these personalized assistants merge with the evolution of robotics and all that to do something more for humans? What do you think?
I think it is a very good idea to found a startup company for toys, okay? So you can put a humanoid robot, and then you ask a question, you have a large language model, and then you say, you ask some question about, where is the banana? And then the humanoid robot will go there and pick it up for you. So this kind of capability will be there. I think it's just the matter of time, right? So Doraemon will come one day, I think, it's really a matter of time. So perhaps one of you in this room, the students, they'll create one.
Good. We look forward to that. All right. So, but before that, I think it's right on time for us to head to lunch soon. So with that, I'd like to ask all of you to thank the speakers again for this very interesting section. And I'll pass back to the MC.
Thank you. Thank you, Professor Lam and Professor Chan. Please remain on stage. And may I invite all the speakers and moderator of this section to come to the front for a group photo. May I invite Professor Lam, Professor Ai, and Professor Chan, please. Okay, thank you very much. Ladies and gentlemen, we will now break for lunch. The next session will begin at 1:30 p.m. For those attending the luncheon, please follow our helpers to the restaurant. A light lunch will also be served in the foyer for registered participants. You can enjoy it in this conference hall, in the foyer, or in the beautiful area of Science Park. Please use the room in the front to lift this room, or use the front door to go to the foyer. Thank you, and see you at 1:30 p.m. A kind reminder for those attending the luncheon, you can follow our helpers to the restaurant.